learners. I am Mrs. Katrina Javier Naldosa from Pasay City North High School M. De La Cruz campus, and I will be your general mathematics teacher for this first quarter, week 6, day 4. And our objective for this lesson is to solve real-life problems using exponential function. Let's start by having the model for exponential growth. And that will be represented by the function y is equal to ab to the x, wherein a is the starting number, or what we call also as the initial number, b is the growth factor, and the exponent x is the intervals. Number of intervals, we could say it's minutes, days, years, so on. So let's have the first example. In a petri dish, there are initially 300 bacteria. If a bacteria grows at a rate of 25% each day, how many will there be tomorrow, 2 weeks from now, or 1 month from now? So let's start by solving for tomorrow. That will be represented by the equation y is equal to ab to the x, wherein our a is equal to 300 because initially there are 300 bacteria. B is equal to 1.25 because it says 25%. And since it's a growth factor, we always add 100%. And for our x, that would be 1 day. So let's now substitute the values. We have y is equal to 300 times 1.25 raised to the first power. And we have y is equal to 375. That is tomorrow. How about 2 days from now? Or 2 weeks from now, rather. So we have x is equal to 14. Since we have 2 weeks, we just need to substitute it to our equation. Y is equal to 300 times 1.25 raised to the 14th. And then, we have y is approximately 300 times 22.74. That came from the computation in the calculator. We just estimated to hundreds. Therefore, we could say that y is approximately 6,821.21. But we could not say 0.21 as a number of bacteria. So instead, we can conclude that that will be 6,821 only. Okay, so next, we have 1 month from now. So that would be x is equal to 30. So we substitute it. Y is equal to 300 times 1.25 to the 30th power. And we compute for the exponential expression. We have y is approximately 300 times 807.79, which gives us 242,338.07. And of course, we could not use decimal numbers as a number of bacteria. So instead, we say that that would be 242,338 in 1 month from now. So those are the values. This is an example of a problem using exponential growth. Let's have the next example. Let's have exponential decay. So for the exponential decay, we have the model function y is equal to a times 1 over b raised to x, where a is the initial number, 1 over b is the decaying factor, and x is the number of intervals. One example would be half-life. In half-life, the b is always equal to 2, and our interval is represented by t over t, wherein the small t is the mean lifetime, wherein the capital T, or the denominator, is the half-life. Let's have the problem. Suppose the half-life of a certain radioactive substance is 10 days, and there are 10 grams initially. Determine the amount of substance remaining after 20 days. So given the mass is half every 10 days, we could say that y sub 0 is 10 grams. That is the initial number. We have this equation. Y is equal to y sub 0 times 1 over 2, because it says half-life, times t over t. And for our small t, our mean lifetime, we say 20 days. And for our half-life, we have 10 days. So that is now substituted. Now let's solve. We have y is equal to 10 times 1/2 to the second power or squared. And then we could say y is equal to 2.5. So we could now conclude that the amount of substance after 20 days is 2.5 grams. Next problem. This is about money, but this is the exponential function. Neil deposits 50,000 pesos in a savings account. The account pays 6% annual interest. If he makes no more withdrawals and deposits, what is his new balance? After 5 years, or maybe after 10 years. So before we solve it, we must know what is the formula that we use for this kind of problem. So we use A, or the accumulated amount, is equal to P times the quantity of 1 plus RT, wherein that is still modeled by the function y is equal to AB to the x. So we have, for the value of P, we have 50,000, or the principal. For the B, we have 1.06, because as I have said before, it's always additional of 100% to the rate. So that is 6% plus 100%, which is 1.06. And for the time, we have 5 years. So let's now substitute to the formula. A is equal to 50,000 times quantity of 1.06 to the 5th power. You may now use your calculator. And we could now get approximately 66,911.2788. But we need some centavos, so we need to round it off to nearest hundreds. The new balance will be 66,911 pesos and 25 centavos after 5 years. Now let's find out how about after 10 years. So same formula, but different value of time. So we have A is equal to 50,000 times 1.06 to the 10th power. You may now use your calculator, and you will get A, or the accumulated amount, is 89,542.3848. We could now conclude that the new balance will be 89,542 pesos and 38 centavos after 10 days. Now let's have another problem, still about money. But this time, it's a different situation. Dexter invested 60,000 pesos at an annual rate of 5% compounded yearly. Find the amount in the account after 10 years if no withdrawals and deposits are made. In this case, this is not a simple interest, but instead a compound interest problem. So we have the formula. A is equal to P times the quantity of 1 plus R over N raised to NT. So let's have our values, or our given values. For the principal, we have 60,000 pesos. And for our annual rate, we have 5%. And for our time, we have 10. So let's now substitute the values. A is equal to 60,000 times 1.05 to the 10th power. Now use your calculator, and we will be getting A is equal to 97,733.6766. Or, in other words, there will be 97,733 pesos and 68 centavos in the account at the end of 10 years. Now let's have the last example. Determine the amount of money that will be accumulated if 100,000 pesos is invested at an annual rate of 8% compounded continuously after 10 years and no withdrawals are made. Take note of the word continuously. So this could be represented by the function A is equal to P times the natural base E raised to RT. So we could now substitute the values. The principal is the 10,000. And For the value of natural base E, that would be approximately 2.71828. For the rate, we have 8% or 0.08, and for the time, 10 years. You may now use your calculator, wherein you could see here the natural base E. And we could get 100,000 times 2.2255409, or 222,554.09. Therefore, there will be 222,554 pesos and 9 centavos in the account after 10 years. So let's sum it up. Real-life problems using exponential problems involves the following. So let's start with exponential growth. Exponential growth refers to the pattern of data that shows sharper increase over time. Example, population growth, just like the bacteria, and compound interest. Next situation would be the half-life of radioactive substance, where the half-life of a radioactive substance is the time it takes for the half of the substance to decay. A quantity is subject to exponential decay if it decreases at a rate of proportional to its current value. And lastly, we have the rule for exponential growth and for the principle. So the rule for exponential growth can be modeled by y is equal to ab to the x, while the rule for exponential decay can be modeled by y is equal to a times 1 over b to the x. Lastly, when the principal p is invested at an annual rate r in percent and compounded continuously, the amount of A accumulated after T years is given by the formula A is equal to P times the natural base E raised to RT. And that ends our lesson for today. Did you understand it very well? If not, you may still go back to the lesson presented in your module. If today's lesson is very clear to you, congratulations! You may now start answering the exercises in your module. Good luck and God bless!